All right, so here I'm going to be going over the FRQs that we had for review in preparation of the test. What I'll be doing is just going over the most important details. The detailed solutions, you should be able to find it within AP Classroom. So I did enable that feature towards the end of class where it gives you the scoring guidelines and sample responses to the problems. So let's just get right to it. Here we have the first one where we have a ball. It's being thrown upward, and there's a resistive force here that is equal to negative B times V. All right. For this problem, I'm going to consider up positive and down negative. And it says here for part 1 that you have to derive an equation for the velocity of the sphere by solving a differential equation and express it in terms of the constants provided. Now, all you're going to have to do for the test is set up the differential equation. Okay, you do not have to solve. So you don't have to solve. All right. If there's a follow-up that requires the solution to differential equation, I will provide it. Okay, so let's analyze our system. I'm going to use Newton's second law, and I know that F net is equal to ma. Because I'm going to be calling up positive for this problem, let's look at our free body diagrams. So I already started kind of working on it, but I had to restart the video. On the way up, right, so at t equals 0, we know that we have the gravitational force pulling down. And because the ball is moving upward, right, it has an upward velocity when we throw it up, there's also a resistive force equal to B times V also going down. And at some later time t, you can see the free body diagram here. We have the resistive force, now it's going up, and the force of gravity is still going to be pulling down towards the center of the Earth. The resistive force is going to be opposite of the velocity. So if this object's moving up, the resistive force is going to be pushing down. If the object's falling down, the resistive force is going to be pushing up. All right. Now, in terms of setting up your differential equation, I already know that you all can do this, right? Looking at Newton's second law. So setting up your equation for Newton's second law. And the only thing you have to do is understand that the velocity and the acceleration are directly related in the sense that acceleration is the first time derivative of velocity. So instead of a, you're going to write dv over dt. All right, so here you can see I have mdv over dt equals negative mg minus bv. And then I just keep the dv over dt. I just keep it on one side of the equation. And this is all you're going to have to do. All right, so if you're setting up a differential equation and not solving it, this is the initial setup. All right, now in the solutions, they do provide the step-by-step analysis, right? So in terms of separation of variables and actually evaluating the integral, and they have the solved differential equation. I don't want to test on that yet, simply because you haven't covered this topic in calculus yet. By the time we revisit first order differential equations, you will have covered it by then. So we're going to look at this topic again in term 3 when we talk about capacitors. And at that point, hopefully we're a little bit more familiar with the process. But for now, this is all you need. What I highlighted here in blue, what I boxed here in blue, just setting up, it's Newton's second law. And instead of a, you're going to write dv over dt, and that's sufficient. If there's a follow-up question where you need the differential equation, it will be provided on the test tomorrow. All right? So this is like the actual differential equation. So now let's look at the second part. Here, part 2, we have to actually sketch the acceleration as a function of time. All right, and now here, TH, as it says in the problem, TH is when it reaches a maximum height. All right, here, so the sphere reaches its maximum height at time TH. All right, so something that you need to know when you're at max height here, right, so this height over here, this is going to be TH. Okay, so at TH, the vertical velocity is 0. All right, and if you think about it, this really makes sense. When the ball is moving upward, when it's on its way up, it has a positive velocity. When the ball is on its way down, it has a negative velocity. So when it's at the max height, it's right in the middle. Between positive and negative, it's 0. The vertical velocity of a free-falling object, when it reaches its max height, it's going to be 0 as it transitions from moving upward to moving downward. So that's a critical piece of information that you need. All right. So at max height, at TH, max height, we know the velocity is 0. So if I draw a free body diagram, the only force I have acting on the object is gravity, right? So mg is equal to ma. I can write the equation again for the acceleration. I have it up here. I know the acceleration is equal to negative g minus b over m times v. Negative g minus b over m times v. But in this case, v is 0 when you're at max height. So I just have negative g. So what I'm going to do is, as we graph the acceleration, I'm going to plot some critical points, and I just need to understand what the function looks like. All right, so I know that at th, the acceleration is negative g. At an earlier time, t0, right? Again, let's look at our net force equation. We see that it's going to be negative g minus b over m times v. Well, it's the same thing here, right? So at this time here, I have negative g minus b over m times v, and I know that v is going to be positive at t equals 0, right? Because it's on its way up. So if v is positive, then this whole term, right, negative g minus b over m times v, well, that means that's going to look like this, right? And this little part here is the negative b over m. You don't have to write that on the graph. I just want to emphasize it, right? So if you look at the scoring guidelines for the graph, it's just that you show that the initial velocity, the initial acceleration, has a magnitude that's larger than gravity, and it's going to be negative. All right, and then I know that this sphere, as time goes on, okay, this is when you have to actually look at the differential equation. So here, I'll just write it down. So it's going to be given. Let's see here. So here, the solution for a differential equation is v naught plus mg over b times e to the negative b over m times t minus mg over b. Okay, that's the actual solution of the differential equation. And at time th, we know that this velocity has to equal 0. Okay, so if we look here at the equation, right, let's think about what the velocity is going to be doing. Right, at t equals 0, let's look at t equals 0. At t equals 0, v is equal to v naught plus mg over b. Now this part here, the e to the negative b over m times t, well, that's just e to the negative b over m times 0, which is just e to the negative 0, right? E to the 0, okay? E to the 0 is equal to 1, all right? So this whole expression is just going to be multiplied by 1 at time t equals 0, minus mg over b. And then if you see here, the mg's over b's cancel out, and this simply states that at t equals 0, the velocity is the initial velocity. Go figure. That's what initial velocity means. Now, at a much later time t, so at later time t, let's say it's much greater than 0, right? As t approaches infinity, now we have to look at this exponential term, the e to the negative b over m times t. I'm going to have e to the negative b over m times infinity. Well, e to the negative infinity, that's equal to 0. All right, so when you have the solution, the solutions to these first order differential equations, there's always going to be some e raised to the power of, right? E raised to the negative power of something times t, all right? Well, e to the 0 at t equals 0, you know that's equal to 1. And then e to the negative infinity at some much greater time, right? So at a much later time, we know that it's going to be, that value is going to be approaching 0. So in the same sense, here we understand that the acceleration due to gravity will also be approaching 0. Well, hold on, let me make sure that's clear. So here at let's look at the differential equation. So I know that at t equals, at some time much greater than 0, this whole expression, right, the v equals v naught plus mg over b times e to the negative b over m times t, this whole expression is going to trend to 0 because e to the negative infinity, that's equal to 0. And then all we have here that's left is the minus mg over b. That's going to be the terminal velocity. Okay. Now, when you're at terminal velocity, you're no longer accelerating, right? Because you've reached the maximum speed. You're falling down in a resistive medium, okay? The air is pushing up on the ball, right? So this is when my resistive force is equal to the force of gravity, and my net force is 0. That's what terminal velocity is. If my net force is 0, my acceleration has to be 0. All right, so I know this acceleration is going to trend towards 0. And now time to actually draw the graph. So we're going to have this curve, and it has to approach this horizontal asymptote. All right, where the acceleration, as it reaches terminal speed, the acceleration of the ball is going to approach 0. All right, so some critical points to note here. You have an asymptote at 0. It's going to approach 0. You know that at time th, at max height, there's no resistive force acting at the ball because the vertical velocity is 0. So, the air's not pushing on it at the very top. And then at t equals 0, initially, the acceleration of the ball is actually going to be larger. The magnitude of the acceleration is going to be larger than just gravity because both the air resistance, the resistive force, and the gravitational force are both pointing downward at t equals 0. Now, the next part, so we have to derive an expression for time when the sphere reaches its maximum height. So for this one here, in the interest of time, I want to go over the critical parts. So you can just see the solution. All they do here is they understand that the velocity is equal to 0, all right, at maximum height, and then you just solve, right? So if the differential equation is provided and it's asked that you have to figure out what the velocity is, at what time th, what's the time th, you have to solve for t. Well, I know the velocity has to be 0, and I just have to solve the equation, right? So here, they isolate the e to the negative bt over m, and then they use logarithms to actually extract the th, right? So this is an important property of logs. This is just algebra, so you do need to know this. So if I have some equation, e to the x equals c, right? Where c is just some constant, okay? The way I can rewrite this expression to solve for x, okay, what you need to do is the inverse of the exponential of e to the x is a logarithm, right? In this case, it's log base e. So this is for whatever exponential function you have. Here I have log base e raised to the power of c equals x. All right, so if I rewrite this expression, I have x is equal to the natural log of c. And you can do that for any exponential function, right? Say I have 10 to the x equals 100, right? Well, we already know that x equals 2, but let's use these rules to kind of rewrite. I'm going to do log base 10 of 100 is equal to x. So it's like saying what power, to what exponent does x have to be such that 10 to the x equals 100? Well, I know that x is equal to log base 10 of 100, which is going to equal 2, okay? So I just want to cover that because it might be some time since you've seen the exponentials and natural logs and whatnot, but that's what they're doing over here. They have e to the negative b over m, okay? So this part here equals this ratio here, and then they just do some reorganization using the properties of logs. So like one example is if you put a minus sign in front of the log, you can just flip the ratio, right? And here we have th equals m over b times natural log of this whole expression. And that's how you solve that one. So I'll just get rid of that. Let's look at the next one. So here we have the, all right, there we go. So here we have the second FRQ. We have a mass 4m and another mass m. This is just a modified Atwood's machine where it's on an inclined plane. And what we need to do is we need to draw a free body diagram, all right? So this is very important. These questions are worth quite a few points, right? I think this one's worth, let's look at the scoring guidelines. Yeah, it's worth 4 points, okay? Don't mess up your free body diagrams, All right, take it slow, double check, make sure you get it right, because free body diagrams are worth a lot for not that much work. It doesn't take that long to draw a free body diagram. You just have to think about what's going on. All right, so let's draw our free body diagram. I know that the block on top of the inclined plane, there's going to be a normal force that is perpendicular to the plane. There's going to be a force of gravity that is, going down. And here we see that there's a tension force pulling along the plane, right, at the same direction of the inclined plane. So I'm going to label that force of tension. All right. Now for block B, all we have is just tension. So force of tension and the force of gravity. Notice that I draw, if this system's going to be accelerating, is there any friction here? Negligible friction. So there's no friction, and the system's clearly going to be accelerating. So one important detail is that you notice how I drew the force of gravity for object B to be larger than the tension force? Well, it should be that way because block B is accelerating downward. And then here I draw for block A, the force of gravity should be larger. I mean, it's a larger block. I mean, technically, I should make it much larger, right? At least 4 times larger. But the fact that it's just simply larger, I mean, there's only so much space. That's important that you got that detail. So now let's look at the scoring guidelines just to double check to see what they're looking for. Wait a minute. Oh, actually, I missed it. This one's only worth 3 points. But still, it doesn't take much effort to get 3 points. So here that you drew the gravitational force on both blocks are directed downward, that you correctly labeled the normal force on block A and it's perpendicular to the dashed line, and a correctly labeled tension force with no extraneous forces. Okay, so those are easy points on the AP exam, right? Even if you're not sure how to approach the problem, which you should be able to do all the problems, but just in case, definitely draw the free body diagrams. Okay, those are worth quite a bit for not much effort. Here, let's look at the rest of the problem. So we have to derive an expression for the magnitude of the acceleration after the blocks are released. Express it in terms of m, theta, and other physical constants. Okay, well, after the block's released, the way they approached it on the scoring guidelines, they just used the systems approach, right? So they looked at all the external forces acting on the system, and they knew that the system was going to accelerate together. I'll do the same, simply because it's a lot easier that way. So we're going to look at this entire system. Okay, so this entire system here, the only external forces acting on the system, okay, is the force of gravity acting on MA and the force of gravity acting on MB. So MBG and MAG. Now, in terms of the direction of the acceleration of the system, MAG is going to be acting at an angle. All right, so here you're going to have to look at the components that are actually going in the direction of the acceleration. So this interior angle here is also theta. This here is the opposite side. So this component here, the component that's actually going in the direction of the acceleration, is MAG times the sine of theta. And it says here that, does it say what? Oh yeah, so block A has a mass of 4m. So that's going to be 4mg sine theta. All right, that's going to accelerate the system in this direction. All right, that's a force that's going in the direction of the acceleration. And then the other force going in the direction of acceleration is MBG. That's just mg. All right, and now we're going to look at our whole system, our 4m plus m system. Okay, so the net force on that system is just going to equal the external forces acting on the system. So here the tension is perpendicular to the acceleration, so that doesn't affect it. Same is true for this this component here for the gravity, the mg cosine theta. That doesn't directly affect the acceleration of the system. And then the tension in between the objects, those are internal forces. All right, so you can do it by looking at individual free body diagrams. This is just faster when you use a systems approach. So here I have mg, right? So that's going to be the force of block B plus this component of the force for block A. Now the reason it's a component is because block A is on an inclined plane. All right, so only a component of the gravity of the weight of block A is going in the direction of the acceleration. So I'm going to put 4 mg times sine theta. All right. And that's basically our setup. So what is it asking for? Oh, so I got to do magnitude of the acceleration. All right. So you have 5 ma is equal to mg plus 4 mg sine theta. All right. And what I can do is I can divide everything by 5m. So then I have a is equal to g plus 4g sine theta, all divided by 5. And that's the answer. All right. So they go through the derivation over here. Yeah, 4 sine theta plus 1 over 5 times g. All right, so they also factor out the g. So you can do that as well. So if you factor the g in both terms, so you can factor that out. G times 1 plus 4 sine theta over 5. Okay. Now let's look at the rest of the problem. Here we have part B. Oh, we just did part B. Part A was just doing the free body diagrams. Now we have to sketch a graph of the magnitude of the net force as a function of the inclined angle theta for each of the following, block A and block B. All right, so this is very interesting. What I recommend doing with these kind of problems is try to think about what the acceleration of the system is at the extremes, right? So let's imagine that theta was 0 degrees. So when theta is 0 degrees, it's just on a flat surface, okay? So the blocks are going like this. This is when theta equals 0. Okay, when theta equals 0, I mean, we can still use the same expression, right? So we have A is equal to G times 1 plus 4 sine theta over 5. Okay, well, the sine of 0 is equal to 0, right? So then when theta equals 0, the acceleration is equal to, well, the sine of 0 is 0, right? So it's just g over 5. All right, but now it's asking about the net force. All right, so the net force is equal to ma. So do we have to do both for each of the following objects? Label a curve for A and B as appropriate. Okay, so I know the acceleration of the system is g over 5. Okay, I know that net force is equal to ma because that's Newton's second law. So what I'm going to do is, let's use different colors. Okay, so I'm going to do the acceleration of A. All right, well, it's equal to ma times, hold on, let me fix that. So I know the acceleration of A is just g over 5, and the same is true for the acceleration of B. But now this graph is asking about the net force, right? So I know that the net force is equal to, so net force acting on A is equal to the mass of A times its acceleration, right? Which is the g over 5 when theta equals 0. So we know that mass of A is 4m, right? So mass of A has a mass of 4m. So I'm going to put 4m times g over 5. Okay, so when theta equals 0, the net force acting on A is 4 over 5 times mg. Okay, so I'm going to just plot that point now so we don't forget. So I'm going to do mass A, I'm going to do in green. Okay, that's 4 over 5 mg. Right? And then for mass B, let's do, we'll do it in blue for mass B. The net force acting on B is equal to mass of B times A. And then so it's just going to be m times g over 5. All right, so I'm going to put that right around here. All right, that's the initial net force acting on object B. Now, in terms of the maximum, okay, let's see. So now we're going to look at when theta equals 90. So when theta equals 90 degrees, I know that the sine of 90 is equal to 1. Okay, so now let's evaluate the expression. The acceleration of the system, in this case, is going to equal g times 1 plus 4 over 5. That's just 5 over 5, g times 5 over 5, which is just g, right? So the acceleration is equal to g. That's basically, that should make sense because if you think about it, say that this block here, now the table's completely vertical, okay, and is being pulled down by the smaller block B. Well, they're going to both accelerate at g, right? They're just going to be in free fall. So basically, these two blocks are just going to be falling straight down. So it makes sense that the acceleration of the system is simply g. Okay. So if the acceleration of the system is g, that would mean that the net force acting, let's do the same argument here. The net force for object A is equal to 4m times g. And then the net force on B is just mg. All right, so we're going to graph those. I know that B is going to have a maximum net force acting on it equal to mg. And then A is going to have a maximum net force equal to 4mg. And then when I actually graph the curves, well, I know that it's going to be roughly proportional to sine theta, right? So it's going to have the rough kind of roughly the same kind of shape as sine theta. In other words, it's going to be a curve that is concave down as it approaches its maximum value. Okay? And then, I mean, if we kept going, then it would start going downward, but you get the idea. So that's important too, is that you draw the curve. The curve, don't draw a line because it's not a linear function. The sine of theta is not a linear function. It's going to follow this curve. It's going to look like a sine curve. So yeah, anyways, that's pretty much it. That's the answer here. If we look at the scoring guidelines, we see here, they're not really sticklers about anything. Yeah, they just care about the initial and the final, right? So understanding that the final net force on object A is 4mg and the initial is 4 over 5 mg. All right, so let's see here. That's interesting. Even if you, even if the starting point was different, yeah, they wouldn't even take a point off. Yeah, because they only care about that A always has a larger net force acting on it than B. So sometimes the scoring guidelines are a bit generous. They're not super sticklers. But let's do it right. Okay, so we understand that the initial net forces for both objects is going to be less than mg. And then for part D, describe how the force or how the graph for block A would change if the string of block B was removed and block A were released from rest on the incline. So for this one, if there's no block B, then the initial acceleration would just be mg sine theta, right? So if I look at the function, this was the original function, 1 plus 4 times sine theta divided by 5. If there's no block B, then the acceleration on the system would just equal g times sine theta. So if theta were 0, right, if I only have block 4 with the block of block A, which has a mass of 4m, when theta is 0, the acceleration, the net force acting on it is going to be 0. And then when it is at 90, it would still have a maximum value of 4mg. Would change if the string in block B were removed and block A were released from rest on the incline. The only thing that would change, it would still have the same maximum value, but its initial value when theta equals 0 would have to be 0. All right, and that's pretty much what they say here. So it would start with 0, all right, because there's nothing pulling it, okay? And it would still have the same maximum value of 4mg, and that's basically it. So now, okay, so I had to cut off the video just because of an interruption. So here's the third FRQ. Now, what I want to focus on when discussing this FRQ is simply the idea of having springs in series and having springs in parallel. So we did cover this in the spring lesson, but just to review, let's say, before we even start talking about this experiment, so let's say I have a spring of 100 newtons per meter, has a spring constant of 100 newtons per meter, and I apply a force of 10 newtons, well, that spring should displace about 0.1 meters, because we know that the equation for a spring is F equals kx. Okay, so I have a spring constant of 100, and I apply a force of 10 newtons on it, well, it should displace a tenth of a meter. Now, what's interesting is that if I take two of the same springs, both of the spring constant of 100 newtons per meter, and I put them in series, so one after another. All right, so here I have a spring. At the end, I have some string, and then I attach another spring to it. It has the exact same spring constant. These springs are going to displace the same amount, right? So say I apply 10 newtons of force. I hang 1 kilogram off the end of the spring. Well, that 10 newtons of force is going to be transferred through the spring. It's going to be pulling on the string at the top. The tension in the string is going to be 10 newtons, and that 10 newtons is going to be pulling down on the other spring that's on top. So the 10 newtons is kind of transferred throughout the entire system, okay? That will actually change the spring constant. So if I have two springs, one after another, okay, the effective spring constant for this whole system, well, the total displacement of the springs, the top one's going to stretch 1/10 of a meter, and the bottom one's going to stretch 1/10 of a meter, okay? So here, K effective is we have the 10 newtons of force being applied. This system of springs, two identical springs in series, they're going to stretch 0.2 meters in total. And so the effective spring constant is going to be 50 newtons per meter. And if I were to do this with 3 springs, right? So if I had 3 springs, 1, 2, 3, okay, they're each going to stretch of 1/10 of a meter, right? So my total X is going to be 0.3 meters, all right? And then the effective spring constant is going to be, say I applied 10 newtons over, and it stretches 0.3 meters, then the spring constant is going to be 33.3 newtons per meter. Okay, so what I'm trying to convey with this problem, or at least with the springs in series and springs in parallel, the spring constant isn't like a fundamental quantity that's associated with the properties of the spring. So let me kind of reiterate that. It doesn't necessarily depend on or at least not like directly on the thickness of the spring or the number of turns. I could have 2 identical springs made of the same steel with the same thickness and the same number of turns per unit length. But if one spring is simply longer than the other spring, okay, in terms of the proportion, but that it stretches, right? So it's going to stretch the same proportion, right? Say I have a spring that's 1 meter long and it stretches 10% of its length when there's like 100 newtons applied to it. Okay, if I have the same exact kind of spring, same metal, same number of turns per unit length, same thickness of the spring, but it's simply longer, well, it's going to stretch more. Okay, so the spring constant of that spring is going to be smaller. All right, that's all this equation is trying to show. All right, and you can set up this equation for any number of springs that are identical. In terms of like the actual problem, so for our tests tomorrow, and just like basically all the tests that we're going to be doing, I'm going to have to treat lab questions as like a separate thing. So I'll have this as like a separate kind of activity where we focus on solving these kind of lab questions, because the issue is these lab questions are the ones that take the longest on the AP exam. They're going to take longer than 30 minutes. And we simply don't have the time to have that as part of our unit assessment. Okay, so these lab questions are going to be a separate kind of assessment. And I still need to organize exactly how I'm going to do that on which labs, right? So I kind of want to set it up with a lab that we're going to be doing in class that's going to be based on an AP problem. But we'll have this be its own separate thing as part of the labs that we'll be doing. What we'll be doing for what we need to know for the test tomorrow is this basic concept. So I highly recommend that you review the lesson that we had on springs. And you review the topic questions associated with it, because they also did springs in parallel. Like say if I took a spring and I cut it in half, what would the new spring constant be? Or if I take that spring, cut it in half, and put them in parallel to each other, definitely go over those topic questions. I'm going to be fairly brief when I go over this problem. So, but basically, in terms of procedure, you're just verifying the equation, and you're given a bunch of springs that are identical, and you need to see if this equation holds. So what I did for my procedure is basically, whenever you're writing a procedure, you want to specify what tools you're going to be using, right? So it has to be detailed enough that another student can replicate it. And you want to include any steps to deal with uncertainty and use equipment that's normally found in the physics laboratory. So you'd mention, I'm going to use a meter stick. I'm going to measure the natural length of the spring. I'm going to measure how the length changes by hanging different masses off the spring. Okay, those masses are going to exert different forces, right? So if I have a 1 kilo mass, that's going to exert 10 newtons of force on the spring. And then say I have a 100 gram mass, that's going to exert only 1 newton of force on the spring. And then you can measure how the springs stretch. And then from that, you can get the spring constants of the individual springs. And then you can get the spring constants of combinations of springs, right? So you do multiple measurements, average them out. You'll have your spring constant for your different combinations of springs, and then you can see if it matches with this equation, right? So hypothetically, if all the spring constants for the springs were 50, you measured the individual springs and you see that it's 50 newtons per meter. Well, if I have two of them that are in series, that combination should have a spring constant of 25. Okay, so that's basically it for the procedure. For part B, how you can analyze it. Well, that's actually there was interesting responses from the example problems. So one of them actually mapped it out and they created a plot where it's they graph 1 over n on the horizontal, and then they put the equation for the springs in series, and you should get a linear fit for the data. Here, what we're going to do is, the reason that works, again, I don't really want to go into it because I'm going to be spending too much time on this particular problem. But the reason that works is because if you have multiple springs that they all have the same spring constant, and you're adding up the individuals, like, so say I have K equivalent for 3 springs, okay, and it's equal to the sum of n of 1 over K for the individual spring constants, right? Well, if I have 3 springs, right, I'm going to do it for n equals 3. Then I have 1 over K plus 1 over K plus 1 over K, and that equals 1 over the equivalent spring constant. And let's say they're all 100, which we did here in this example, right? Say I had 3 springs in series, right? Let's see how that comes out. So you'd have 1 over 100 plus 1 over 100 plus 1 over 100. That equals 3 over 100. And the equivalent spring constant, KEQ, and then the equivalent spring constant would be 100 over 3, which is what we expect. All right, so that would verify the equation, right? If you made a plot of the equivalent spring constant versus 1 over n, you should get a direct relationship. And that just has to do with how the equation is set up. But personally, I think it's just better or easier to think about if you just compare, right? So you have this equation, you have these expected values for the spring constant based on the equation, and then you have the measured values, and then you compare them. And if they're approximately equal to each other, then you can make the claim that this equation is valid. For the next one here, where it gives you a non-Hookean spring, this one's not terribly tricky, but you have to kind of know what you're doing. It's asking for you to produce some data and what quantities that you could graph in order to get a straight line that could calculate the experimental value for K3. So ultimately what you want to do is you want to get K3. So I have this expression here. You know what K1 is. It says here it's 10 newtons per meter. All right, so if you want to measure K3 or you want to calculate K3, what you're going to want to do is you're going to want to set it up so the slope of that line is equal to K3. In order to set it up so the slope of the line is equal to K3, that process is called linearization. I'm going to have to, for my vertical axis, I'm actually going to want to put f minus K1 delta x, right? So all I do is I rewrote this expression so it follows the equation for a line, y equals mx plus b. We're not going to worry about the y-intercept for now. But the fact that the slope of that line is equal to K3, what we're trying to calculate, that's just how you have to set up the equation, right? You need to get K3 times your independent variable, which in this case is how much you stretch the springs, right? So on the horizontal axis, you'd want to put delta x cubed, okay? And then on the vertical axis, you'd want to put f minus K1 delta x. And then if you plot that data, the slope of that line will give you K3. And I'm not going to plot the data now because in the interest of time, we're not going to do that. But basically, in the solution manual, they actually calculate it. So this is why these kind of questions take so long, is because you have to actually go through and perform the calculations, right? So you'd have to look at the data that's given. You know that
k is equal to 10, you have these values here for the different amounts that the spring stretches for different delta x's. And then you'd want to create your new vertical and horizontal axes and actually perform the calculations. So it can be fairly time consuming, and then actually plot it on the graph, label the graph, put in the values, measure the slope of the line. That's a lot. Okay, we don't have time to be able to do that while assessing everything else. This has to be its own kind of assessment, right? Which we'll get to at a later time. But yeah, anyways, the biggest takeaway for this problem is this idea. I want you to review the lesson we had on springs and looking at springs in series and springs in parallel. Because simply having a longer spring or having two springs in series, that changes the effective spring constant of the system. So let's look at the last one. This one's a good problem. It also has a differential equation, but I'll talk about it. Here we have this varying applied force. So this time it's interesting. There's no resistive force. It just has a varying applied force that has this decaying exponential term. So let's look at part A. So if the rough surface could extend as far as necessary, would the box come to a complete stop in a finite amount of time? Justify your answer using qualitative reasoning beyond equations, though you may refer to a given equation for FA at T. So for this one, I do write out an equation because that kind of is guiding your qualitative explanation. So you have to think about what's going on. Basically, what this equation is saying is that we start off at T equals 0, right? So at T equals 0, my force applied is just equal to F naught. So I have some initial force applied. And then as time goes on, when T equals, say as T approaches infinity, right? That's a much later time, T much greater than 0. Okay, well, this decaying exponential term is going to keep getting smaller and smaller, right? Until it's going to be approaching 0, right? So the force applied approaches 0, basically is what I'm trying to say. So the force applied is going to approach 0 as the time approaches 0. That's what this equation is telling us, right? E raised to this goes back to what I was saying earlier. E raised to negative infinity is 0. E raised to 0 is 1. And that's how you want to kind of like understand what these equations are saying. Because there's a coefficient of friction, right? There's kinetic friction acting on the system. I can draw a free body diagram here. So I have my force applied. This is going to change over time. I got my normal force going up. That's going to be equal to the force of gravity. This is not an incline or anything like that. And then I have my friction force going against the system. So the force of kinetic friction, that's going to equal mu sub k times normal force, right? So mu mg. Okay. So what we can do is we can write an equation for the net force, and that tells us how the motion is going to change. So I know that the net force, right, the things that are acting in the direction of motion, in the direction of the acceleration of the box, is applied force and the friction force. So my net force here is going to equal my force applied minus the force of kinetic friction, and that has to equal ma, right? If I want to write a full expression, I can write ma is equal to this equation for the force applied, F naught times e to negative beta t, or bt, minus the friction, which is mu sub k times mg. All right, that's my expression. So we need to figure out if this box is going to come to a complete stop in a finite amount of time. All right. Well, my net force, if F naught is greater than the force of friction. Actually, does it even specify that? It doesn't matter. It shouldn't matter, but the applied force varying with time. Technically, it doesn't even matter. But what's important is that we know this force is decreasing, right? So this applied force is decreasing. You're pushing a box, and I'm decreasing the amount of applied force I have on the box. Well, eventually, the net force acting on the box is going to be going the other way, okay? And the box is going to be decelerating. If the box is decelerating, right, its velocity is decreasing, at some point, the box is no longer going to be moving, right? And you can see this. You push something and you decrease the amount of force that you're pushing on something. Eventually, the thing's not going to move anymore, right? Because the friction force is going to be greater than the force of you pushing. It's going to decelerate to a stop, and then it stops. All right, so that's the reasoning you can use to, identify that this box will eventually stop. What I wrote down specifically, I said it will slow down to a complete stop. The applied force is decreasing with time, and it will eventually be less than the friction force. At that point, the box will decelerate, and it'll eventually come to a complete stop. All right, that's all you need. You need to write the equation, but I think it's a good idea to have the equation guide your reasoning. All right, derive an equation for the velocity v. All right, so now I have an equation for the net force on the box, and I have to write an equation for the velocity v. Again, in the interest of time, I'm just going to pull up the solution manual. So yeah, they have this equation here for the acceleration. We know Newton's second law. It's equal to net force. The acceleration is equal to net force divided by m. Here is the expression we have for net force divided by m. And then they set up their differential equation, right? So if we have a problem tomorrow where you have to set up a differential equation, you would stop at that point. Solving a differential equation, you're not going to have to worry about that for the test tomorrow. But they show you how to do it. So you separate your variables, you perform the integral, you have your bounds of integration, v naught to v, 0 to t, and then you evaluate, and then you end up with this equation here. So if we had any follow-up questions, that would be given on the test we're going to have tomorrow. So I would give you the solution to the differential equation. Part C, what's part C saying? So justify if the equation for velocity that you derived in part B is either consistent or not consistent with your reasoning in part A. Well, let's actually look at the equation. So it says here, let's kind of analyze what's going on. At time t equals 0, let's see what it says. So at t equals 0, I know that my velocity is equal to v naught plus f naught over mb times, well, e to the 0 is equal to 1, right? So this term here is just 1 minus 1. Well, 1 minus 1 is 0, okay? So this whole thing's going to disappear at t equals 0. So I can just erase that. So I have v naught minus mu sub k times g times t. This is also 0. Right, so this t is 0, this t is 0. So basically at t equals 0, my velocity equals v naught. Hopefully that's obvious. So this equation does work out, right? But I start with some initial velocity. At some later time t, okay, let's say t is very large. Well, when t is very large, I know that this e to the negative bt is going to approach 0, right? So e raised to t as t approaches infinity, or at least that t is much greater than 0, this is going to approach 0, okay? So eventually what you end up with at some later time, t much greater than 0, basically what we have is v naught plus f naught over mb. Okay, that's my initial applied force acting on the object, minus mu sub k times gt, where t is some later time much greater than 0. So if we look back at our reasoning, we know that eventually this thing's going to come to a stop. And it's going to come to a stop when this term dominates this term. All right, so this term I have is positive, this term I have is negative, and basically when it gets to a point where the velocity equals 0, right, so when v equals 0, how long is that going to take? Well, I have here t is equal to negative v naught minus f naught over mb, all divided by negative mu sub k times g. And yeah, so at this time, this is when the velocity is going to be 0. All right, and that's follows what we reasoned in part A, right? So seeing what they say, yeah, so the amount that the friction force is going to be changing the velocity. So I start with some initial velocity. If my applied force is greater than my friction force initially, the velocity is going to increase, right? But then eventually, as my applied force decreases, at some point, the net force acting on the object is going to be negative as the friction term is larger than the applied force, and it's going to decelerate until it eventually stops. All right. So yeah, that's pretty much it. I think the hard part with this one is actually solving the differential equation. But again, for the test that we'll be having tomorrow, all you need to do is set up your differential equations. We'll focus on differential equations at a later time once you cover it in calc. And I guess the only other piece of advice I have, so we have these FRQs, and I kind of went over the important details. Definitely check out your topic questions. So those topic questions that we've gone over, review them. They're going to be helpful. And then obviously just review your notes. And you can just email me if you have any particular questions. I think the test is very fair that we're going to have tomorrow. It's not everything that's on the test is stuff that we've covered before. There's not going to be any curveballs, and as long as you understand the content, you should do very well. All right, so